All right. So, hello. I'm here to talk about how AI can significantly augment predictive maintenance practices of mobile mining equipment. I am Kevin Urbanski, CTO and co-founder of Rithmik Solutions. And at Rithmik, we leverage AI for predictive maintenance of mobile mining equipment. So the topics that I'm going to discuss today, first I'll start off by level setting on what I mean by predictive maintenance, so we're all on the same page. And I'll talk about the power of AI in this space and how to exploit these powerful tools to enhance maintenance and reliability. And I'll go into the application of these tools and what it looks like in reality, how to begin an AI predictive maintenance journey, and then if there's time, I'll go over what an AI data pipeline could look like physically and from a software perspective. So as I was mentioning, I'd like to level set on the phrase predictive maintenance because not everyone has the same understanding of what it entails. So during this presentation, when I say predictive maintenance, I'm talking about maintenance and reliability decision-making that is based on predictions made about the operating state, efficiency, and/or health of the equipment. And the distinction that people can get hung up on is the fact that these predictions aren't always about the future. They could be also about the present or past. And I'll get into how that past predictions are beneficial in a few slides. So why AI for predictive maintenance? It turns out that AI is really good at taking information that is available and generating new data and hidden information. So in other words, it's really good at making predictions. And obviously for predictive maintenance, you need to make predictions. The reason for the ability to do this is recently with the cloud compute power and affordability of cloud compute has been driving the algorithms in this space. So they're getting better. They're doing their thing better, and there's also an abundance of data in mining, so and other applications as well that allow these algorithms to learn and get better. So in maintenance, not only is there a lot of data collected from over the years, specifically in mobile mining equipment, it just so happens that reliability and maintenance problems can be framed as prediction problems. So the end result of running these algorithms and using AI is increased yield in production, minimize downtime, avoid costly repairs, extend asset life, reduce fuel consumption, and the byproduct of all this is lower byproducts, so lower CO2 emissions. So within the mobile equipment space, the data available for predictive maintenance is the OEM sensor data. So this equipment often has hundreds and sometimes even thousands of sensors that are that the data can be collected from. And the equipment also has OEM alarm information that can be very helpful when building these models. There's also the contextual information from the site. So work order information often has a history of the repairs that have been completed on the equipment, components that have been replaced, and also the dollar values of the work that's been done is great for assessing the value of the models. And there's also the fleet management and dispatch software has a lot of information that's extremely helpful for contextual information, and any other equipment health and system like vibration analysis, fuel consumption analysis, and oil analysis. And AI is extremely good at looking at vibration analysis. It's using the same sort of techniques that are used for speech recognition. It can pick out some really neat things from vibration data. And there's also any application within predictive maintenance that would benefit from images or video that could be used to help as well. So before going into what AI-driven predictive maintenance looks like in application, I just want to talk a bit about a few of the AI methods that slot nicely into the workflow. A number of these key approaches are the ones listed on the screen here: digital twins, anomaly detection, and as well as classification. So with a digital twin, that's a word that's been floating around a lot lately, and a buzzword of sorts. What I mean by, and it means different things to different people. So also what I mean by predictive or what I mean by digital twin during this presentation is it's a model that captures a machine or component's operating characteristics. So this could look like capturing the optimal running of a Komatsu 930E-4. And what you can do is, when you capture those conditions, you can run that model alongside the actual asset and monitor for deviations. And these deviations, the information out of these models is very powerful on their own, but they're also powerful in that they can drive other further analytic opportunities and other algorithms. And AI specifically opens up the opportunity for trainable, really deep multivariate digital twins. And what I mean by multivariate is you have the ability to do things like look at the RPM, the velocity, the payload of a truck, and predict what the oil pressure should be. So under all of those different combinations of values, you can come out with an idea of what you can get a really good model to compare your actual asset to. So the other method, the second method I have is anomaly detection. And these algorithms are good to pick up on when something is not right, and they do it in a really fancy way. Again, they can be multivariate and look at the relationships between thousands of sensors and data points simultaneously to pick out what is when something's not right. And the third method that I have here is AI for classification. It can classify when and if a component will fail. It can do things like classifying if a filter needs changing. This is more of a prescriptive approach, whether bearings are deteriorating or a pump is cavitating. Or it could be just identifying when something's running normally or better than normal. So the techniques that I just spoke about can be used for the following opportunities, which are earlier predictions of impending failures, deep insight about equipment health and efficiency, root cause analysis, consumption or consumable wear and tear of part and part performance, as well as other embedded opportunities. So the first one, so those of you who aren't versed in reliability speak, this graph on the right here is a graph taken from the book Reliability Centered Maintenance by John Mowbray. And it outlines a progression of a failure mode. So it shows the point at which a failure starts to occur, the point at which it can be found and identified or predicted, which is the point P. And then there's the point F, which is the full functional failure when a piece of equipment is no longer doing what it's supposed to. So the interval between the P and F is called the PF interval. And this is the time that you have to predict or to know that something's going wrong. So the AI can extend that interval, that PF interval, and doing so, you can avoid consequences of predicting or progressing failures. And that comes with safety and economical implications. And earlier equals more time to act. So you stop equipment from full catastrophic failure. Or you can even, if the period interval is long enough, you can schedule in the specific failures in the next PM or even PMs after that if you have a long enough period. So the next method is this, the digital twin can drive many valuable things. As I mentioned, it can give a view into health, efficiency, and overall operation of the equipment. So it's possible to create health indicators like you're seeing on the screen here of equipment and components. And this allows you to do a variety of things. You get a fleet snapshot. So what needs attention, what will need attention. And then you can get on top of developing issues before they become urgent. You can leave good running equipment operating and pay attention to what needs attention. And this kind of leads into better end-of-life planning. So if you have a piece of equipment or a component that's scheduled to be decommissioned or taken out of service, if it's actually operating okay, you can get more life out of it. So when indexes show issues or inefficiencies, you can dig into what is happening. So if your digital twin outputs the specific deviations that are being experienced on specific sensors, you can use those to dig into what's going on. So on the screen, you can see that there's might be hard to read, but on the right, there's a cursor that's showing that the oil pressure is deviating by 5 index points above what is expected during the operating conditions. So this is over a 2-week period. And you can see that all of a sudden the oil pressure is just uncharacteristic. It's not operating as is expected. So this can be used by mechanics for better understanding issues or troubleshooting before actually heading out to the equipment to fix things. And this is also extremely helpful for reliability engineers for root cause analysis. When you have a collective history of the predictions, and this is what I was saying, how you can make predictions about the past. So you can predict, say if you have 10 years of data, you can run a model on your entire 10 years of data and have those predictions and just totally zoom out and look at the progression of that equipment over time and pick out where there was issues and just have a deeper understanding of what was going on with that equipment throughout its life. And the other opportunity is the fact that there's mountains. If you have mountains of data, like say 10 years, and you have hundreds of sensors to look at, the AI can pick out what to focus on, where to put your attention. And it also can help lean out OEM alarms. Sometimes OEM alarms can be quite chatty, and knowing which ones are the important ones can help with that. The other opportunity too is the wear indicator indexes for consumables. So a few examples are could be monitoring the bit on a blast hole drill, which doing so could help with more production, safer and lower cost semi-autonomous and autonomous drilling. You could also use it to look at the performance of air and oil filters, tire health, and as well as extending hour-based PM schedules. So if there's certain components that tend to be replaced on a certain amount of hours, if you can get some sort of health metrics on them, you can actually schedule based on condition. So, and the other opportunities, the fact that the data has embedded in it, if there is an operator on the equipment, the operator's behaviors is automatically embedded in that data. And there's also the surrounding environmental conditions that are embedded as well. So the opportunities here is looking for behaviors that damage the equipment or are better, more efficient or less fuel consumption activities. And on the environment, you could look at things like the road conditions on struts, the air quality on operation, and the temperature on efficiency. But these same things that are opportunities are also what makes doing predictive maintenance on mobile mining equipment challenging because of the diversity in operator behavior, temperatures and weather, the topography, landscape, material. So there's a lot of diversity that you need to be able to distinguish out as to be able to make the insights valuable. You need to be able to know what's happening and what's causing what. So when to bring an AI into predictive maintenance. These are two quite busy graphs about, the one on the right is a typical that we've seen.
Kevin, can you, oh, there you go.
You can see it?
Yes, we can see it.
Okay. Cool. So on the left is a company that's been collecting data for a while, and what typically happens is when they started data collection, they did some cleaning using manual processes, just looking at the data, and then setting up some user-defined events, such as like looking at when RPM is a certain level and oil pressure is a certain level. Should we sound an alarm? Those types of kind of manual threshold settings. And then, so then if they want to bring in analytics, there's kind of like another, you start looking at the data with the analytics, and it quickly picks out if there's holes in the data, if the data quality is actually not as good as expected, if there's like specific problems that you're looking to predict, the AI will quickly point out if there needs to be more data augmentation. So maybe more sensors need to be installed to be able to do what you're doing. So as opposed to on the right, where this is a company that's starting data collection and also starting the analytics at the same time. So you can, if you start early, you can actually get into filling those holes right from the beginning. You don't have the advantage of having the big history, a long history of the data to work with, but you'll still be able to fill those holes, some of the holes that are visible at that point with the smaller amounts of data that you got. So it could eliminate more change management if you get the earlier that you have it in place, and better data earlier, which means quicker to prescriptive maintenance practices. So this last slide here is just a general, really high level data pipeline of what an AI data pipeline can look like. And there's many ways to do this, and it depends on the application at hand. Yes, this example here is on the right, there are 3 data collection devices. So it could be, say, a haul truck, a drill, and a shovel. And they're feeding their data that's being collected into this. This is a data streaming, or a data bus. So the example I'm using here is Kafka, a piece of software that can do this. And so what Kafka or data bus allows is for different applications to be guaranteed to get the data that they want or need to do what they're doing. So here the data is, time series data is being stored in this time series database. The relational data is being stored in the relational database. So this is the first component of AI in the top right corner, this analytics engine. So this is where the models are built. So typically, or it's ideal to run the analytics engine in the cloud, because the cloud is very flexible. For example, one of the things we're working on required to do a lot of computation that would have taken over a month to do with a single CPU. And in the cloud, we're able to fire up 3,300 CPUs and 7 terabytes of RAM, all at effectively the same time to complete that calculation in 30 minutes. And not only those types of extreme cases, but just when you're training AI models, you can, if you're running in the cloud, you can fire up hundreds or thousands of models to different iterations of the models to get to your best model as quick as possible. But that said, the analytics engines don't have to be run on the cloud. They can be run on premise. You can buy a lot of compute power to do so, or they can also be run on the edge, but that doesn't happen very often and not needed very often. Oops. Then there's also the AI prediction generator, so that's where you run your actual models that after they're trained. So it takes the data as it's coming in, and it generates the predictions that you're going to be using for your maintenance practices. And if it's something that needs to be, if the predictions need to be used in a timely fashion, you can just feed that data right to your visualization, or send an email or notification out about it. or if it's not so urgent, you can just write it back to the database to be looked at in the future. But if things are really urgent, you can run the prediction generation right on the devices, the data collection devices. So on the right, I have the first top one and the middle one, which are also generating predictions. So the top one could be an autonomous piece of equipment that needs the predictions to be generated on the computer on board so that they can be used to control the piece of equipment. And then the middle one could be a drill that, if we're looking at some sort of health and safety, we're looking for some sort of failures that could be dangerous. We could feed those sorts of that sort of information just directly to the display as soon as the prediction results are completed. So, and that's my presentation. If there's any questions after the question period, feel free to reach out. And here's my email. And thank you guys very much.
Thank you, Kevin, so much for your presentation today. Let's go ahead and give a round of applause. Do we have any questions for Kevin at this time? You can also unmute yourself and speak, or go ahead and share it in the chat.
Hey, Kevin, this is David Haukenes from Komatsu Autonomous. I was just wondering, what's your perception on how OEMs can contribute to these data pipeline initiatives and making sure that customers are well positioned to do this in the market? Do you find that the largest problems are in the formatting or the lack of labeling and data generation? How can OEMs help their customers by giving them data that's well prepared to move into initiatives like this?
Yeah, definitely. I guess the biggest thing that we see is the customers still are having trouble getting their data. So like just acquiring the data at the frequencies they want it, and as well as getting it in good quality. Like we've seen a lot of the data gaps, for example, just like not really collecting it as it could be collected. So I guess OEMs really being clear on the protocols, helping the customers implement, or the data collection companies implement those the protocols to collect the data as best as they can. Interpretation of alarms is also another one that would be very helpful. Yeah, I guess providing as much information about the information on the equipment and how to get it as possible.
Perfect. Thank you. I see we have 2 questions on the chat right now. The first one comes from Brent. Have you developed any scheduling tools for condition-based maintenance to avoid multiple units requiring maintenance at the same time?
We don't have scheduling tools created. Right now, we are integrating with scheduling tools. It is within our pipeline. We're working towards that.
Perfect, thank you. And looks like we have another question. Can you give us an example of the product service you're offering to the mining companies? What kind of data do you usually need?
Sure. So we have a couple of things. So our products are, we built our own analytics engine that is specifically tailored to ingest the type of data off of the equipment and to be able to generate models, site-specific models really quickly because there's so much diversity across all the mines. So we built it to tailor the model specifically to mines. And we also have a suite of different approaches and algorithms that meet the challenges with the data. So basically and the type of data that we get that we need to do this sorts of analytics are the OEM sensor data, the alarm and event data off of the equipment, and as much contextual information that a mine has. Like if they have a dispatch or fleet management system, getting access to that data is extremely helpful. Weather information, and as well as any other health monitoring system that helps with labeling the data. So basically, we're a product company that basically set people up for success in predictive maintenance. And we integrate with the thing I should mention is we integrate with the company's current visualization software. So instead of having another screen to look at, we look to integrate with whatever software they're using.
Perfect, thank you. I have a question here from Walter. What tools do you recommend to start predictive data analysis working in mining?
Oh, what tools? That's a really tough question to answer, I guess, because there's such a diversity. It depends on exactly what you're doing. I would say number one is definitely work in the cloud. Leveraging cloud computing it's game changing. It's definitely the way to go. And there's so many tools out there. Like for example, the programming languages have these libraries like TensorFlow that can do some really advanced algorithms. Like there's an algorithm that just came out not too long ago called Transformer that is going to be a game-changing, or already is a game-changing algorithm. And you can run that very complicated algorithm just by using some of these programming packages. So yeah, it's a hard, I guess that's the start. It really depends on what you're trying to do.
Perfect, and we have, I think, 2 last questions. It looks like there's actually several. So if we don't manage to go through all of them, Kevin, I might send you the questions offline, and then we will add it to the outcomes of the call. What kind of business benefit you see for a company to adopt condition-based maintenance? Is there a number? Oh, I think President, I think this is more, I think you can contact Kevin directly if you want a quote. So I think that Kevin actually shared his contact details, and maybe we can also connect you with him afterwards. Then back to the OEM question, why is it so difficult to get the sensor data that you need and at the frequency that required? Very interesting, because we actually have a project going about this one.
I guess it doesn't have to be difficult. It's just that having the information that you need to be able to collect the data, to write the software or to go to I guess you just have to, the people that are building the drivers have to have the know-how, how to develop the technology and work with the hardware to be able to do it in an optimal fashion. So it doesn't necessarily, it also, I guess I should mention, depends, it's equipment to equipment, like different protocols and different interfaces are more difficult than others. Like some are really straightforward and some are more complicated. Like some manufacturers actually still don't share that information. So some people actually had to go in and reverse engineer some of these ports to actually get that data. And when you have to do that, you don't necessarily always totally understand all of the limitations. So it's also kind of a big question.
Yeah, definitely. Actually, GMG has, we published a guideline a few years ago, and we're working on another one that is mobile equipment open data sets. Open data sets, I think it's not that name particular, but it's basically getting those data sets of the mobile equipment. So if you want to get on board, just send me a message and we can get you engaged in the project that is just getting started. And the last question before we move into the last breakout room, how much impact you see the AI optimized maintenance can deliver compared to the regular maintenance practice in the availability of assets?
How much? I guess I see that it's going to have a big impact on, well, it's going to have an impact on the way things are right now. It's really going to have a huge impact on autonomous equipment, because you're not going to have the people sitting, you don't have the people sitting on the equipment and sensing the specific issues as they're happening. I don't have exact numbers. I can provide those. So if you shoot me an email, I can provide that information. I don't have it on hand right now.
Perfect. Thank you, Kevin, so much for your presentation today. It was